Hello Year 12, welcome to our third video here for networks. Okay, previously we've learned some basic things about networks, what an edge is, what a vertex is, what the degree of a vertex is, some of those things. And in our second exercise, we looked at Eulerian trails and circuits, remembering those things and the conditions that apply to them. Now we're going to look at this idea of a minimum spanning tree. So first of all, a tree is a network that has no cycles, right? There's no sort of completely fenced off area. There's no sort of enclosed areas. So that's what a tree is. A spanning tree, right, is a tree, a subgraph of my network that visits, that includes every vertex. Certainly not every edge, right? Certainly not every edge, but it connects every vertex. And finally, a minimum spanning tree is where I have a weighted network. It is a spanning tree that has the shortest total weight. Okay, so it uses the smallest or shortest edges to create that spanning tree. Right here. Well, let's have a look at some examples. Which of the following subgraphs represents a spanning tree of this network? This one here, is this a spanning tree? First of all, does it close off any areas? Does it have any cycles? No, it doesn't. So the first condition is fine. Two, does it connect every vertex? Yes, it does. So that's a big yes from me. Second one here, is this a spanning tree? It's not a tree, you see, because I've got this cycle, right? It's all closed up. So no, not that one. This one here, it is a tree because there's no closed off area. And it visits every vertex, so it is not just a tree, but a spanning tree. So that's a yes from me. Over here, again, while it sort of looks as though this is closed off, it's not really. Okay, there's no vertex here. So in fact, these two subgraphs are very similar. So this is also a spanning tree. Now this one here, I have a tree, but it doesn't connect. It's not a spanning tree. It hasn't connected this vertex. So not this one. Okay, two of them up. Now, moving along again, what do we got? To find a minimum spanning tree, we can use an algorithm. Now, an algorithm is a clever kind of a thing. It's a process of repetition, usually, a set of instructions that you follow to achieve some desired result. I'm going to introduce you to Prim's algorithm first. Now, we use Prim's algorithm to identify a minimum spanning tree, and what you do is you start by choosing any vertex in the graph. Right? Now, that's not going to be a problem in itself because my minimum spanning tree has to connect. Right? To be a spanning tree, it has to connect every vertex. So the vertex that I choose will have to be part of any spanning tree. That's good. The next thing we do is we choose the shortest edge that is connected to that vertex. Okay, and that makes a tree, a very small basic tree, a tree of one edge that connects two vertices, but nonetheless, that's my tree. The next step, and most of the, and the following steps until we're finished basically, is find the shortest edge that is connected to that tree that doesn't form a circuit or a cycle, and add that to our tree. So we're going to continually grow our tree until we have connected every vertex. Let's have a go at doing that. Here I have a somewhat complicated network. I'm going to use a highlighter to do this. Now it says start wherever you like. I'm going to start here at E. It doesn't matter. Now from here I choose the shortest edge connected to that, and that will be this one here. So that's my first step. Second step, I need to connect onto my very basic tree here with the shortest edge that doesn't form a cycle. That's my 4. Okay, the next one that I'm going to join right? I've got to sort of scan around. 13, 10, 8, 6. Oh, there's a 3 over here. I'm definitely going to put that one on there. Now the shortest thing that's connected, 13, 10, 8, 6, 9, 8, 11. It's going to have to be this 6. That's my shortest edge at the moment. And now I think the shortest thing will be a 5. And finally, this 5 here. Okay, and that is my minimum spanning tree. You can see that I have connected every vertex together. And the length of my minimum spanning tree, or the weight of my minimum spanning tree, is 5 plus 5 plus 6, 16, and 3 is 19, and 4 here is 23, and a 7 will have a minimum spanning tree of a weight of 30. Right, using Prim's algorithm. Choose any vertex, and then gradually add the shortest vertex, the shortest edge that doesn't form a circuit. Right, Prim's algorithm. There is another algorithm that we could use called Kruskal's algorithm. Kruskal's is slightly different. Here you start by choosing the shortest edge, and you keep adding edges, right? You keep adding edges whether they are connected or not. You just find the shortest edge that doesn't create a cycle, and you keep doing that until you have your minimum spanning tree, until you've connected every vertex to a tree. So let's have another go. We need to start by choosing the shortest edge, right? That's going to be the 3 up here, right? So first of all the 3, and then this 4, and then I've got a couple of 5s. I've just got to keep an eye open that I don't form any cycles. Right, 3, 4, 5. The next shortest one is a 6. Right, now it's not quite finished yet. You can see I've got nearly every vertex. Haven't got this vertex here in. Right, once I've hit the 7, I have my minimum spanning tree, and I'm done. That's using Kruskal's algorithm. So Prim's starts anywhere and is always connected. Kruskal's starts with the shortest edge and keeps adding the shortest edge every time can be, right, and not connected, disconnected as we go along. That is the idea of a tree, a spanning tree, a minimum spanning tree, and these two algorithms, Kruskal's and Prim's. Well, that's the end of this introduction to the exercise. It's time to get stuck in now and do some of them. You know what to do if you've got a question. Jot it down, ask me in class. See you then.